Alrighty, howdy folks. Let's look at chapter 6, section 3. This is trigonometric functions of different angles. Uh, where did we stop last time? I think we talked about the trig function values for 30 degrees, 45 degrees, and 60 degrees. Now we are going to learn about the trig function values for a few more angles. Cool? Okay. So earlier we found the trigonometric ratios of right triangles. Specifically, we found the trig ratios of angles 30 degrees, 45 degrees, 60 degrees. Okay. So a simple question, right? What about 0? What about 90? And to further, what about trig ratios of angles greater than 90 degrees? Right? Does it make any sense? Say, what's the sine of 120 degrees? Simple, right? Draw a right triangle with one of the angles to be 120 degrees. You're done. Are you done? Did you see the trick in that question? Did you fall into the trap of that question? A right triangle with one of the angles of the right triangle being 120 degrees. Is that possible? No, right? Because in a triangle, the sum of the interior angles should equal 180. One of the angles is already 90, so the sum of the other two angles must be equal to 90 degrees. So if a second angle is 120 degrees, gone, right? There is no way. So we cannot use that kind of method, like drawing a right triangle the way we did for the previous one. So we need to have a different approach for it. That's the point I'm trying to make here. Cool? All right, let's move on. Consider the right triangle that is placed in the Cartesian plane as shown. Yeah. So this time what we'll do is we are actually doing something like an analytical trigonometry. Okay. Let's say we have a Cartesian plane, XY system, basically, x-axis and y-axis like this. Oh, by the way, I need to point out something. Oftentimes, you see at a high school level, the people draw the x-axis with an arrow here on the right-hand side and another arrow on the left-hand side. That's wrong. Similarly, they will draw an arrow up here and also an arrow down. That's wrong. The arrow has to be on only one side for each of the axes. That is because there is some significance to the arrow. When we put an arrow here, we are saying values increase in that direction. Let's say this point x is equal to 0. As we move towards the arrow, values are increasing. So if we start with 0 here, 1, 2, 3, 4, 5, 6, so on. That's the idea. Similarly for the y-axis. Oh, come on. What's the big deal about that? Oh, it's a real big deal. Because pretty soon, some of you engineers, when you take a class called statics or mechanics of materials, you would be dealing with something like what's called a beam, deflection of a beam. And in the deflection of a beam, you set up XY coordinate system just like this. You would have a beam is the beam, think of a diving board. In a swimming pool, you see a diving board. Think of that as a beam. Okay, and you can analyze that beam by setting up x and y coordinate axis. And typically what people do, engineers do, is put that y coordinate pointing down, which means any deflection downward is considered to be positive. And so if that beam happens to bend up, you will say, ah, that had a negative deflection, which would be weird. What? Negative? When it moved up? Yeah, we can set up our coordinate axis any which way we want. But we have to be consistent. The arrow must indicate the direction in which things are increasing. Okay? All right. Anyway, let's move on. So we have a Cartesian coordinate system, and basically we have a point P whose coordinates are x and y. The moment I locate a point in with using the coordinates x and y, what do I mean by I located the point here? That means from the origin, the x distance happens to be x, or the direction, the distance of that point in the x direction happens to be x. And the same point in the distance in the y direction from the origin happens to be y. So that's why this point has coordinates x and y. As we have seen, that is the x distance and this distance is y. Okay, and this is definitely a right triangle. So this line is making a 90-degree angle with the x-axis. Okay, next. This angle, let's call it as theta. The angle made by the segment, this line segment, with respect to the x-axis is theta. And because we are measuring it counterclockwise, positive theta. But then the question becomes, what is this r? That is the distance from the origin to the point. Can we figure out that r? In other words, the hypotenuse of this right triangle? Yeah, the moment we say hypotenuse, we can use Pythagoras theorem and say r must be square root of x squared plus y squared. Okay, so that's the stuff that I have discussed here. And the moment we do this, now we can say, okay, what is sine theta? Sine theta, in the last section we learned, is opposite over hypotenuse. What is opposite here? Opposite is y. Hypotenuse is what? R. So sine theta is y over r. Can we say that? Yes, we can say that. Now, you might say, oh, come on, man. What's the big deal about that? Why do you have to switch to this stupid x and y? Weren't we perfectly fine with calling this as the opposite side and this as the hypotenuse, and sine theta is opposite over hypotenuse? Why do we need this x, y, and r and all of this? That's a good question, and the answer is forthcoming. Okay, let's continue with this thought, and I'll show you why switching to this way of understanding is of great utility. Next, cosine theta, as you can guess, is adjacent over hypotenuse, which means x over r, and tangent theta is opposite over adjacent, y over x, provided x is not equal to 0. And cosecant theta is hypotenuse over opposite, the reciprocal of sine theta, or over y, provided y is not 0. Secant theta is r over x. Cotangent theta is x over y. Okay, so stuff that I hope is fairly clear to you. I don't have to spend a whole lot of time. Okay, now here is the beauty. To find the trig ratios of 0 degrees, what can we do? Theta should be apparently 0, 0. Okay, if this angle is theta and that theta is 0, when would that happen? That would happen if this segment falls right on top of this. Would you agree? If that segment falls right on top of the x-axis, then the angle theta would be 0. Oh, okay. Now, if that is the case, what if we placed the point P at, say, 1? x value 1 and y value should be 0, because every point on this x-axis will have a y value of 0. And for x value, let's pick 1. Okay. Then we could place the point P at 1, 0. Then x equals 1, y is 0. And what is r? R is square root of x square plus y square. That is square root of 1 square plus 0 square, because x is 1, y is 0, we said. And so that's equal to 1. Cool. Can we use this now to find sine of 0 degrees? Yeah. Sine of theta is y over r. Don't say opposite over hypotenuse at this stage. That's the idea. Use the concept of y over r. And sine 0 is y over r. Y is 0. R is 1. So 0. Is it really true that sine of 0 degrees is 0? You bet. What is cosine of 0? Well, cosine is x over r. You need to memorize this with an understanding. Okay? X over r. What is x? X is 1. R is what? 1. So 1 over 1. What is tangent of 0 degrees? Tangent is y over x. So 0 over 1, which is 0. So tangent 0 degrees is 0. Now the rest of them, cosecant 0 is 1 over 0. Maybe I should spend some time. Cosecant of 0, we can do, okay, y over r. Cosecant is r over y. R is 1, but y happens to be 0. We have 1 over 0. 1 over 0 is undefined. Okay, there are no two ways about it. Well, what my friend said, 1 over 0 is infinity. Forget it. 1 over 0 is undefined. End of the story. Cool. What about secant 0? Secant 0 is r over x. So 1 over 1, and that's also equal to 1. Cotangent of 0. Cotangent of 0 is x over y. That is 1 over 0. And that is undefined as well. Cool. So we found the trig ratios of 0 degrees by using this. Then what? How about 90 degrees? Maybe, can I get you to tell me what to do? For 0 degrees, theta is 0. We put the point here at 1, 0. We made the x to be 1 and y is 0. For 90 degrees, where is this line? This line should be making 90 degrees. So it should be, would you agree that it should fall right on top of the y-axis? Cool. Every point on the y-axis has an x-coordinate of what? 0. Let me repeat that. Every point on the y-axis has an x-coordinate of 0. Oh, okay, cool. What should we pick for y? We can pick any number, but without any loss of generality, let's pick 1. So we'll put the point P at 0, 1, and then go through a similar analysis. Cool. That's how we'll find all the trig function values for 90 degrees. And when we do that, 0, 1, x is 0, y is 1, and r happens to be square root of x squared plus y squared, which once again turns out to be 1. And sine 90 degrees is y over r, and that is 1 over 1, which is 1. Cosine 90 degrees, cosine theta, is x over r, and that's going to be 0. Tangent of 90 degrees, tangent is y over x. Y over x. Y is 1 and x is 0. Ooh, 1 over 0. Undefined. Cosecant of 90 is r over y. 1 over 1 is 1. Secant of 90 degrees, r over x, which is undefined, 1 over 0. And cotangent of 90 degrees is x over y, that is 0 over 1. and that's 0. 0 divided by 1 is 0. Would you agree with that? Yep, it is. So now we have the trig function values for two additional angles. Earlier we knew the ratios for 30, 45, and 60. Now we know the values for 0 and 90 as well. And why should we place this? What's the big deal about this? Well, the big deal about this X, Y, and R system is, now look at this. Is it possible for me to place the line segment here for theta greater than 90 degrees? Yeah, I can do that. But there is no right triangle here. With this angle, yeah, that's okay. But this time, we will make our right triangle over here. Okay? So this is the idea. So once again, we'll pick a point P, X, Y, but X is going to be this way. In fact, the way I have shown, would you agree? X would be negative. If this is the origin, this is 0, X equal to 0 at the origin. And to the left, we have -1, -2, -3, -4, and so on. So these X value is actually negative in this context. The Y value is still positive because we are going up from the origin in the Y direction. So that is still positive. So the way we analyze trig functions for angles greater than 90 degrees is this way. We will place this line segment at whatever angle we want from the positive x-axis. Here, something greater than 90, located here. And here, P of xy with x less than 0 and y greater than 0 is a point in the plane. It is a point in the plane. Who says x and y have to be positive? X and y could be positive, negative, or a combination. X is positive, y is negative, and all those things. So that's what we're looking at. And still, R would be x square plus y square. Even if x were to be negative, when you square it, that's going to be positive. So that's not an issue. Yeah. Does it make sense? What did I say? Even if x were to be negative, x squared would be positive. You agree with me on that? If x were to be -2, what is the quantity -2 squared? +4, right? So x squared is guaranteed to be positive, and similarly y squared is guaranteed to be positive. So x squared plus y squared is guaranteed to be positive, and we can take the square root of a positive quantity. The thing we cannot do, the thing we cannot do is take the square root of a negative number, which means, to be more precise, when we take the square root of a negative number, we do not end up with a real number. We end up with an imaginary number or a complex number. So we don't want to do that. We want to stay in the real field unless stated otherwise. Okay, so we have r equals square root of x squared plus y squared. Now what is sine theta? Sine theta is still the same thing, y over r. Cosine theta is x over r. Tangent theta is y over x. Same things as before. However, the point I'm trying to make here is we are capable of talking about things like this trig ratios even for angles greater than 90. We retain the same concept as we did when we place the when we place the point P of xy over here with a positive x and positive y. Cool? All right. So that's the idea. The advantage of modified view is that we could let theta be anywhere between 0 and 360 degrees. Okay. Then let's look at a few identities that we end up with. So we know that sine theta is y over r, cosine theta is x over r, tangent theta is y over x. I might be just going, okay, tangent sine theta is y over r is cosine, blah, 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 like that, right? But as I say stuff like this, you got to be able to pause the video, close your eyes. Let me remember. Okay, let me recall, and you should try to recall. Sine theta is y over r. If you're having trouble with recalling that, just in your mind, draw yourself an x and y coordinate system, put a point P with positive x and positive y like I did, and then you draw that right triangle. Oh, okay, that right triangle, opposite of this theta would be that y. You got to do stuff like that. Okay, so sine theta is y over r, cosine theta is x over r, tangent theta is y over x. So what happens if we do sine theta over cosine theta? Why would you do that? I don't know, just for the heck of it. Sine theta over cosine theta. If we were to do that, we have y over r over x over r. Can we simplify that? Yeah, divide by x over r is the same as multiply by the reciprocal r over x. And when we do that, y over r over x over r, we get y over r times the reciprocal r over x. R's cancel and we get y over x. But wait, isn't y over x tangent theta? Yeah. So guess what? Sine theta over cosine theta is equal to tangent theta. Or the other way, tangent theta is nothing but sine theta over cosine theta. And that is what? The fact that tangent theta is sine theta over cosine theta is what? It is an identity. What do you mean identity? What's identity? Well, tangent theta equals sine theta over cosine theta. To me that sounds like x equals 5, y equals 3. Is there a difference between x equals 5 and tangent theta equals sine theta over cosine theta? Yeah, there is. We call such equalities, yes, I agree, tangent theta equals sine theta over cosine theta is an equality, but we call it an identity because it is true for all values of theta. No matter what theta you put, tangent of what? That's equal to sine theta over cosine theta. It doesn't matter. That's the beauty of identities. They are true for all values, provided they are defined. Okay? When cosine theta is 0, you have dividing by a 0. That's undefined. That's a different story. But this is definitely true. Okay, are there any other identities like that? Yep. Note that sine theta is y over r, cosecant. Sine theta is y over r, but cosecant theta is r over y. Y over r over y. This is what I was saying. It's a reciprocal. Cosecant is a reciprocal of sine. That means 1 over sine theta is cosecant theta. That's also another identity, which means for whatever theta you plug, that concept is true. 1 over sine theta would be cosecant theta. And cosine theta is x over r, whereas secant theta is r over x. That means there is a inverse relationship between secant and cosine. 1 over cosine theta is secant theta. Cool. What else? Tangent theta happens to be y over x, and cotangent theta is x over y. Boy, allergies are killing me. Sorry about that. 1 over tangent theta is cotangent theta. These are called reciprocal relationships. All right. So we need to remember one more thing. There's cosine theta over sine theta is cotangent theta. similar idea as this one. Okay, so right away, boys and girls, ladies and gentlemen, we have 5 identities that we must know. Okay, all right. Now with that, let me do a summary. Summary is, if we have theta, and theta takes on all these values, 0 degrees, 30, 45, 60, 90, for each of these angles, is it not true that we found sine, cosine, tangent, everything? So what are those values? Let me put that in a table. And you must memorize all these values. How many values? These many values you have to memorize. What? That, you gotta be kidding me. I got good news. It's really not that difficult, provided you understand a pattern that these things follow. Okay, sine theta. Let's look at sine theta. Sine 0 is 0. But on purpose, I'm going to write that as square root of 0 over 2. Let me repeat what I'm saying. Earlier, we found sine 0 is y over r, y was 0, r was 1, and so sine 0 is 0. But instead of thinking of it as just a simple 0, on purpose, I'm calling it a square root of 0 over 2. Why? Be patient. Cool. Sine of 30 degrees. Did any of you have a chance to memorize that? Sine of 30 degrees is 1/2. But I'm going to write that as square root of 1 over 2. It is actually 1/2, but instead of 1/2, I'm going to write that as square root of 1 over 2. Cool. 45 degrees, square root of 2 over 2. Sine of 60 degrees, square root of 3 over 2. Sine of 90 degrees was 1. But I'm going to write that as square root of 4 over 2. Is that right? Yeah, square root of 4 is 2. 2 over 2 is 1. Now, do you see how easy it is to remember? This is apparently square root of 0 over 2. This is square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. For 0, 30, 45, 60, 90, and for sine. Now, is that simple to remember? Yeah, it is simple to remember. And you must remember this. Okay. All right, man. That seems like a simple thing. I can see the pattern. I can easily do this. But what about cosine theta? Cosine theta is cosine of 0 is 1, which means square root of 4 over 2. Cosine of 30 degrees is square root of 3 over 2. Cosine of 45 degrees is square root of 2 over 2. And cosine of 60 degrees is 1 over 2, but we will write that as square root of 1 over 2. And cosine of 90 degrees is 0, which we write as square root of 0 over 2. I know you guys are clever. You're going, oh my goodness, I see the pattern here, man. Here it's like decreasing. Over there for sine, we had increasing pattern. On the top, we had square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. Now we go the opposite, square root of 4, square root of 3, square root of 2. Yep, you are absolutely right. Okay, so wait, are you saying that cosine of 90 or cosine of 0 is the same as sine of 90? Yeah, and cosine of 30 is the same as sine of 60? Yeah. Cosine of 45 is the same as sine of 45? Yeah, see that pattern. Cosine of 60 is sine of 30. Cosine of 90 is same as sine of 0. Okay, in other words, we'll talk about this more formally, but basically you want cosine of whatever angle, cosine of 0. Wait a minute, cosine of 0, right? 90 minus 0. Make first, because you want cosine of 0, think of 90 minus that angle 0. 90 minus 0 is 90. Then say what is sine of 90? Sine of 90 degrees is 1. So cosine of 0 must be 1. You want cosine of 30? Make it 90 minus, figure out 90 minus 30. That is 60. What is sine of 60? Square root of 3 over 2. So cosine of 30 is square root of 3 over 2. So basically cosine of 90 minus theta is the same as sine theta. Okay, that's why cosine and sine are called cofunctions. Okay, so that's done. Okay, this is fine, but what about tangent theta? And here I'll tell you a secret. I almost never remember tangent values. If you ask me, hey, what's a tangent of 30 degrees? I'm in my head like, give me half a second. Tangent of theta is sine of theta over cosine theta, right? So sine 30 over cosine 30. Sine 30 I know is 1/2. And cosine 30 I know is square root of 3 over 2. So I do this division in my head. 1/2 over square root of 3 over 2. The denominators cancel. So I end up with 1 over square root of 3. That is what I do quickly in my head. If I'm not up to doing in my head, I try not to be macho. Just pick up a piece of paper and write down. Okay, sine of 30, 1/2. Cosine of 30, square root of 3 over 2. Write down, do the division, and come up with 1 over square root of 3. So that's exactly what I did here. 0 over 1 is 0. Sine theta. Sine 0 over cosine 0. That's how I found tangent 0. And 1 over 2 over square root of 3 over 2 gave me 1 over square root of 3. And quite nicely, square root of 2 over 2 over square root of 2 over 2 is 1. Whereas here, square root of 3 over 2 over 1 over 2, 2's cancel, you get square root of 3. 1 over 0 is undefined. So, tangent, all I do is recall what sine and cosine are, and based on that figure out tangent theta as sine theta over cosine theta. Now, cotangent theta, again the same idea. I have no idea what is cotangent. Cotangent of 45, I know that, that's 1. Similarly, for tangent of 45 degrees is 1. But cotangent of 60, I have no idea. I'll simply go, wait a minute, what is cosine of 60? Cosine of 60 is 1/2. Sine of 60, square root of 3 over 2. 1 over square root of 3 then. That's how I do this. Cool. So cosine is 1 over 0, and cotangent is cosine over sine. So 1 over 0, undefined. And for 30 degrees, square root of 3 over 2 over 1/2. Looks like that's not what I did. Well, I used another form. I simply seem to be doing here. I could have done cosine theta over sine theta. That would have been another way of doing this. Here all I'm doing is I'm doing the reciprocal of the tangent. I'm using that reciprocal relationship. So 1 over the tangent of 30 degrees. 1 over 1 over square root of 3 is square root of 3. 1 over 1 is 1. 1 over square root of 3, directly I can write that. Over here, I cannot say 1 over undefined. That's a slight disadvantage of this. What is 1 over undefined? That's equal to 0. You cannot say that. That's not a good thing to do. So that is why for this part you may want to go, well, the reciprocal 0 over 1 or cosine over sine. Cool. And what do we do about secant? Once again, I always use the reciprocal relationship. I wouldn't know what secant of 30 degrees is, but I know cosine of 30. I take the reciprocal and I'm done. So secant 0 is 1 over 1. This is 2 over square root of 3. 2 over square root of 2, which turns out to be square root of 2. 2 over 1. 2 over, 1 over 0 undefined. And cosecant theta is the reciprocal of sine. So 1 over 0 undefined. 2 over square root of 2 square root of 2. Square root of 2 over square root of 3. 1 over 1 is 1. Okay. Like I said, at any time you must remember these values, or like I said, remember the sign based on that trick. Cosine is just the thing reversed in order, and based on that figure out the tangent, cotangents, and all these things. That's it. That will make you very, very strong. All right. I think this is a pretty long video, so I'm going to split this into 2 parts. So let me pause this video here and make it into a part 2, the remaining part. Okay. All righty.